I'm Juliette Chabassier. I'm here as a member of the Modart company that commercializes software Pianotech that you might know, and we also commercialize a software called Organtech. I wanted to show you a little bit Organtech before talking about it. So there's going to be sound, normally. Let me check that yeah, okay. It's not good. I know, okay. I don't do the demo, it's going to take too much time. Okay. I can show you, you can download the trial if you want to try it. Anyway, so our goal is to provide with this software and VST that simulates sound in real time on the normal CPUs with physical modeling. And so here I'm going to talk about organ pipes, and as most specifically reed organ pipes and reed wind instrument, because in the physical point of view they work in similar ways. And the specificity of my talk will be about the fact that we take into account the reed-induced flow. So we try to model this physically. So let's look at the object. So this is, if you have an organ pipe and you remove the foot, this is what you're going to see. So you have this metal bar, it's the tongue, it can vibrate. Then you have the shallot under it. You have the tuning wire that can move. It changes the pitch. It does not change only the pitch. And then there is the wedge here to just take it all together. The pipe would be on the right of the screen here. I'm not going to talk about the pipe today. I'm going to talk about this part of the model, and specifically on how we can adjust the physical parameters to aim at a target sound that we want the software to sound like. So I'm going to show equations now. Don't panic. It's the regular simple model of reed instruments. On the first line you have the displacement of the tip of the tongue, which is modeled by the unknown y, and it's following an oscillator equation forced by a right-hand side term, the difference of pressure, delta P, and this difference of pressure is the difference of the pressure between this point, basically, and this point. Okay. And then you have the third equation, which relates the flow to the difference of pressure. It's a Bernoulli equation. And the term that we want to tackle is this one, the reed-induced flow. And then, of course, the pipe reacts. It's the last equation here with, let's say, an impedance relation between the pressure and the flow at the beginning of the pipe. This is not the subject of my talk. What's interesting here is that many parameters appear, physical parameters, so there is like a collection of 7 parameters. The reed frequency, omega naught, the reed surface, SR, the mass, MR, the effective mass, the displacement at rest, why not, the dissipation, G, the size of the reed, W, weight, the width, and the mouth pressure. And the idea when you do virtual instruments with physical modeling is that you want a value for these parameters in order to launch your simulation and to hear the sound that you want to hear. And it's not easy to predict how the model will react to these parameters. So a good way of reducing this problem is to scale the equation. So in my talk, I will show you how we scale the equation. We did it very classically, following the literature, but we ended up with a new metaparameter that we called kappa, because the other one were called gamma and zeta. And then, so this is the parameter that is interesting because it can control this reed-induced flow. And I will show you how this new metaparameter, I hope, I will show you, stabilizes in some way the behavior of the system regarding with respect to its parameters. And so I will show you the influence of the reed frequency when you have all metaparameter fixed, and then the influence of the new metaparameter that we introduced, and hopefully I will show you cartographies. I will do it on 3 types of pipes. First, a cylinder, so you can think of it as a very crude clarinet. Then a cone, which would be a very crude oboe. And then a vox humana pipe that I wanted to make you hear, but maybe in the end I can make it work. So if you scale the equation, then you end up like with these new equations that are simpler here, where you changed not only the parameters, but also the unknowns has been scaled. And you end up with a collection of meta-parameters, which are gamma, the dimensionless mouth pressure, zeta, which is called in the literature the dimensionless aperture of the reed, and we introduce a new parameter kappa. And of course, you still have the reed frequency omega naught and a quality factor of the reed QR. What's interesting here is that you see that the frequency omega naught appears in the term of the reed-induced flow. This was made obligatory if you want kappa to be dimensionless, actually. So this is what we found out. It's the fact that we have to divide by omega naught here. So it's nice because you see that it's the same equations. You didn't lose anything, so it means that we have reduced the number of parameters necessary to control the system. So there's no loss, but we have less parameters. So when you try to control the dynamical system, it's better. It means that the first one was over-parameterized, right? It means that you can choose several values, different set of values of physical parameters that will lead to the same solution. It's not good when you want to tune a system, of course. So I recall here the definition of these parameters. And I just wanted to mention that in the literature, you can find some people who have tried to introduce this effective length to account for the reed-induced flow, but it's dimensioned, it's in matter. What's interesting here is that kappa is dimensionless. Okay, so I've tried to make a sketch about the equations that relate the physical parameter and the dimensionless parameter here. What you see is that the physical parameter contribute to many actually meta-parameters. But in colors, I've highlighted those who contribute only to one. So they can be like seen like tuners of the meta-parameters. The bad news is that omega naught in the physical world, when you change it, it will change omega naught of the meta world, but it also changes the closing pressure of the reed, and hence the dimensionless pressure and the aperture zeta. So it means that if you freeze all the physical parameters except omega naught and you run a simulation in the non-scaled equations, it will not give you the same behavior than if you freeze all the meta parameters and you try to see how the system reacts when you increase the frequency. And so, we try to see how the system would be more like monotonic with respect to the parameters. So first, in the paper for DAFx, I tried to look at the values found in the literature of physical parameters of these several papers. Here I draw it on a graph, gamma zeta graph, and in color you have the kappa. So what you can see is that most of them is in this square. It's a square, 1, 1. Sorry. So you see that the meta parameters are close to 1, between 0 and 1, except outliers here, because these are all clarinet systems, or clarinet-like systems. This is an organ pipe, and this is a trumpet. So it's funny to see that in this plane you can discriminate instruments. And then if you look at the reed frequency and the closing pressure, you can also see the values of the literature. What's interesting here is to see, so the new information is the color of the point, because it's kappa, and you can see that in the literature, kappa goes indeed between 0 and 1. So it's a good starting point. So now let's see how the dynamical system reacts. Here I show you some result of a linear stability analysis of the system for a cylinder. So it means that at some point you can analyze this dynamical system and know when it's going to go into an oscillation, but it's not possible to predict exactly the frequency of the oscillation and how it will react, but it's a first guess. And so here you have two graphs. On the left, it's a low quality factor reed, so think of it as a cane reed, clarinet reed, something. And here you have a high quality factor reed, so like a metal reed, so more for an organ pipe. Here is the frequency of the reed is moving, and you want to know the sounding frequency of your system. And so the linear stability predicts that there are some frequencies where it will sound. If you do simulations, you indeed recover something which is close to it. And what you see, it's a very known fact, is that you sound close to the resonant frequency from below. Now I want to see what happens when kappa varies. The last slide was for kappa very small, so if you don't take into account the read-induced flow. Here, if you make kappa vary, you can see that the system reacts differently according to the value of kappa. So very low kappa would be this graph with the cross, and when you increase kappa, you go here. And so when you have a low quality factor, you can see that the system overblows if kappa is small, and it doesn't overblow anymore if kappa is big with a low quality factor. With a high quality factor, it doesn't do it. I wanted to make you listen to sounds. I hope it's going to work. I think it doesn't work. Okay. So I can show it later if you want. Then you can do cartographies in order to see how the system reacts. So in the plane gamma zeta, you can, for instance, here see the relative frequency. And you can do it for many values of kappa and the quality factor of the read. So the quality factor goes from left to right, and the kappa goes from the top to the bottom, and you can see how your system reacts on different values of the parameter. And what we have seen is that with the meta parameters, and especially kappa, it is more monotonical than with the physical parameters. This is for the sound amplitude. This would be for the sound deviation in sense. If you look at it as a sound relative frequency, you can see it's not so monotonic. It's not even for a cylinder. So it's funny to see that, as you know, it's not an easy tunable system. Now let's see for the cone what happens. So you have a similar behavior. For the low quality factor, you have less overblowing than for the high quality factor. And let's finish with a pipe organ, which is the Vox Humana. It's a small pipe, and you can see these different behaviors. What's interesting is that in the literature, you see that people say if you want to play a clarinet, you need a clarinet. What is it? It has a high frequency, but the pipe decides what note you play. So it means you're here. And what this graph tells us is that if you want a clarinet, you need a high frequency, you need a low quality factor, but you also need a big kappa somehow. Otherwise, your clarinet will blow up, and it's not the behavior that you want. And of course, for the all different pipes, it works. But since the impedance curve is different, the radioactive zones where you cannot play are smaller, and so you don't necessarily hear it. But it's still an effect that is present. So in conclusion, our non-dimension parameter kappa completes the existing meta parameter gamma and zeta. What we did here was a crude modeling of a reed instrument with no contact term and a lot of very crude assumptions. You see that some playing regimes were highlighted. There is this forbidden zone after the resonant peak. And one of the conclusions is that to play a clarinet, you need two ingredients, a strongly damped reed and a large kappa. Otherwise, you rather have an organ-like behavior. So if you want to try organ tech, you can download the trial and see for yourself if the sounds are nice or not. I'm sorry that I couldn't play the sound. If you want to hear it, you can ask me. Thanks.
Thanks very much. That was a very interesting talk. And well, I'm actually going to start with a question, if you don't mind. Can you go back to the scaled equations that you showed kind of early on? Yeah, exactly. I was wondering, you have that omega naught factor, but could not you rescale time so that that disappears? I mean, I understand that you're running simulations, so you kind of want to have physical time there, but yeah. I was wondering if from an analysis perspective, perhaps it could be useful to have, scale time too.
Absolutely. As you see, omega naught appears in the system before the time derivative with the order which is absolutely the same. So you have omega naught with dot term, omega naught dot term, and omega squared double dot. So you can scale the time and it will go well. What's going to go not well is that here you have to divide the frequency by omega naught. And so it means somehow your read will be dimensionless, but then it's the pipe that has to adjust. And so, as you said, for simulation purposes, you need you can do it. it's interesting to do it. You can understand very interesting things from doing it. But on a simulation perspective, it's not feasible.
So time is the only thing that is dimensional in that system now? Everything else is non-dimensional?
Yes.
Cool.
Exactly.
Questions from the audience, perhaps? No takers?
I can try to make a piano organ take.
Maybe, yeah, we can listen to some demos.
Bah pourtant. No, that's a problem on my side, I'm sorry. Do you hear it? Okay. So, yeah, I try to increase sound, I don't know. My computer thinks it's, I don't know why. It's not my regular. This is an organ. I don't know, I can make you listen to the Vox Humana pipe if you like. You don't hear it. It's really frustrating.
There's an audio cable right there somewhere. Yeah, you can. Do you have
Oh, good. Be careful. I'm doing it again. Just... Oh. Ah oui, du coup, je dois changer le... Ok. Écouteur externe de pourtant. Nice. This is a nice part. Here you hear a clarinet. Here you hear a... let's put Here you hear a flute. And now the clarinet, so it's a reed pipe, the clarinet pipe. And if you want to hear the Vox Humana that I just showed you. So it's well tuned.
Okay, thank you very much.